Hello friends, good evening. My name is Abhishek Kumar and today I am going to start Structural Engineering 1. Dear friends, before starting the subject, we should be known the scope of this subject. As a civil engineer, our aim is to design the structure. A structure has several components, for example, beam, column, slab, foundation. Dear friends, our aim is to design these components. If we talk about beam, so how to design beam? Design means to fix the dimensions of beam, means how much should be depth of beam, how much should be width of beam. So these dimensions are decided on the basis of external loading. Due to external loading, structure starts deform, means structure start to bend, or due to external loading at a section there may be shearing of structure. So but structure do not want to deform, hence some internal resistive forces are developed by the structure to resist the external loading. These internal resistive force are shear force, bending moment, axial force. So the design will be on the basis of these internal resistive forces. How much is the magnitude of these forces? On the basis of these forces we will design the structure. So our aim is to calculate these internal forces. How to calculate these internal forces? Dear friends, in the structural engineering we talk about only static structures, hence equation of static equilibrium are always applicable. So we cut structure at a section and analyze this small part on the basis of these equilibrium equation. So first of all we should be known the external reactions, because then only we can analyze the structure. So our first aim is to calculate the external reactions, and now further our aim is to calculate the internal forces. So let us see how we calculate these internal forces and external reactions. Okay. Dear friends, how to calculate the internal forces? For example, it is a beam. This is a simply supported beam. Simply supported beam. It carries two load. One is vertical load and another is horizontal load P. So due to this loading, reaction will be, if this distance is L by 2, this distance is L by 2, it will be P by 2 and it will be P by 2. Also it is P in this direction, hence one more reaction will develop here. So now we have calculated the external reactions. One is P by 2, other is also P by 2. So we want to find out the internal forces. Internal forces may be shear force, bending moment, axial force. So we cut the section and analyze this section. So this is the section, and the external loading may be this P by 2 and this P by 2. Now we have to calculate the forces, the internal forces. So if we use the equation of equilibrium, so one is summation fx0, means force, equation of equilibrium is summation fx0, means force from this direction equal to force from this direction. So P by 2 from this direction, P by 2 from this direction. Now we will use summation fy equal to 0, means force from up direction to force from down direction. Hence from downward direction it is P by 2 up, so one more force will be P by 2 down. Also one more equation is there, summation mz0. If this point is A, if we write the moment of all the forces about this point, we see that moment of this P is, this P by 2 is 0, this P by 2 is 0, but moment and also of this P by 2 is 0, but moment of this P by 2 will be there if distance is x. So P by 2 into x is this direction, so internal moment will be P by 2 into x. Dear friends, This force which is parallel to the cross section is called as shear force. It is shear force. And this resistive moment which resists the bending of beam is called as bending moment, and this force which is along the axis of beam is called as axial force. So our aim is to calculate shear force, axial force and bending moment. But before calculating these force, we should be known the external equations. So first of all, we will see how to calculate the external reactions. So dear friends, if we talk about the supports, there are different types of supports. If we talk about 2D loading may be 2D or 3D. However, structure is always 3D, but loading may be 2D or 3D. If loading is 2D, then first support is fixed support. Fixed support carries at most three reactions. One will be vertical reaction VA, other will be horizontal reaction, and third will be rotational reaction. So at fixed support in 2D, three reactions may develop. If it is hinge support, so external reaction will be vertical reaction and horizontal reaction. The rotational reaction will be zero. Dear friends, reactions are developed in those direction in which direction the deformations or the deflections are prevented. See, here vertical motion is prevented, so vertical reaction is there. Horizontal motion is prevented, horizontal reaction is there. But this rotational motion is not prevented. This beam can rotate about this point, so rotational reaction will be zero. However, in this case we cannot rotate the reaction. See, this is a beam and this is fixed support. Now if we talk about this point, this neither this can go up nor in this direction and nor this can rotate. Even after I am applied any loading, this point will remain at this position, right? But if it is roller support, now only vertical reaction will develop. Dear friends, on roller support only one reaction appears which is perpendicular to the plane of roller, because this reaction will also be zero. Reason behind is that the deflection in this direction or movement in this direction is not prevented. Roller can move in this direction, so reaction in this direction will be zero. Also roller, it can rotate about this point, so the rotational reaction will also be zero, right? Now if we talk about 3D, if it is a fixed support, so six reactions are developed. And if it is hinge support, three reactions. These six reactions I will talk about later. And on hinge support, three reactions develop, and on roller support again the one reaction will develop. See how we find out how many reactions will develop. See, if we see this a 3D diagram, this is, it is called as transverse axis. It is also called as transverse axis. This axis is called as longitudinal axis, the axis along the length of beam, and these two axes perpendicular to this axis are called as transverse axis. Axis y and x are transverse axis, or we can say this is x, this is z, and this is y. So it is longitudinal axis. These two axes are transverse axis. How many internal forces develop in the structure? First force is this. Dear friends, at most six forces may develop in a structure in 3D loading. What are those six forces? Three are translational force. Translational means linear, in linear direction, and three are rotational force, right? So first force is this Fx, force in x direction. Second force may develop in y direction, it will be Fy. And third force may this Fz. This is Fx, this is Fy, this is Fz. Now this beam can rotate in three directions. See, if this is a beam, one force is this Fx, other force is this Fy, and other force is this Fz. Also, this beam can bend like this. Maybe this beam can bend like this, or this beam can bend like this. So how many rotational forces are there? First is this, it is my, means bending moment along y direction, or I can show here, this is my. Second is mx means this is mx, or I can show like this mx. This is my, this is mx, and also like this it is mz, because this axis is z axis, so it will be mz, right? So these are at most 6 forces. 3 are rotational, 3 are linear, Fx, Fy, Fz, and 3 are rotational, Mx, My, Mz. Similarly, the equilibrium equations in 3D are 6 equations. What are those 6 equations? Summation Fx equal to 0, summation Fy equal to 0, summation Fz equal to 0, summation Mx equal to 0, summation My equal to 0, summation Mz equal to 0, right? Also, now, so if it is hinge support, if at most 6 reactions are Fx, Fy, Fz, Mx, My, Mz, 6 reaction. Now if it is hinge support, so reactions will be 3. If it is hinge, so bending at hinge, bending moment becomes 0. So bending moment will be 0, so Mx, My, Mz will be 0, and only 3 forces will be there, Fx, Fy, Fz, right? Fx, Fy, Fz. But at roller support, only one reaction appear, that is vertical reaction. This roller can move, this is roller, it can move in this direction, it can move in this direction, but it cannot move in this direction, right? So only one reaction appears. This is 1, this is 3, this is 6, right? There is some special type of support, this, it is called as guided roller. This is guided roller, means what is guided roller? There is a plate, on this plate I have welded this, so now it can move in this direction or this direction, but neither it can move in vertical direction nor it can rotate about this point. So bending moment is also, and this vertical reaction Va is there, and this Ma is there, but in this direction this reaction becomes 0, Ha. Dear friends, only 3 reactions are possible in case of 2D. Of these 3 reactions, motion in one direction is free, so reaction in that direction will become 0. And in which direction motion is free? This horizontal direction motion is free, hence reaction will be 0. So of these 3 reactions, one becomes 0 and 2 reactions will appear. So in case of guided roller, in 2D case, only 2 reactions appear, right? Okay, but if loading, sometimes he says loading is vertical only. If loading is vertical, in this case all the reactions, see, if loading in case of statement is like that, in case of beam, if supports are at same level and loading is only vertical, then all the reactions in horizontal plane becomes 0. See, in 3D case, if I talk about 3D case, how many reactions are there? These, see, these are 6 reactions: Fx, Fy, Fz, Mx, My, Mz. Of these 3 reactions, this is the horizontal plane. In this horizontal plane, only 3 reactions are there. One is Fx, other is this Fz, and one this moment My. So these 3 reactions will become 0 and only 3 reactions will be there. One is Fy and 2 are Mx and Mz, right? So in case of 3D, at fixed support, only 3 reactions will be there. So in fixed support 3 reactions will be there. Now if we talk about hinge support, at hinge support, in general 3 reactions were there. Now if loading is vertical only, these 3 reactions were Fx, Fy and Fz. All of these 3 reactions, two are in horizontal plane and one is in vertical plane, right? So these 2 reactions which are in horizontal plane will become 0. See, one is this Fx and Fz. These 2 reactions will be 0 and only Fy will be there. So in case of hinge support, one reaction will be there. Or in case of roller support, if it is roller support, only one reaction was there and that was in vertical plane, that was vertical, so only one reaction will be there. But if we talk about 2D, in 2D, this was 2D and the reactions were like this: one is this, other is this, and third is this. So horizontal reaction in horizontal plane is only this. So in case of 2D, if support is fixed support, so reactions will be 2 only. One is this and other one is this. In case of hinge support, how many reactions were there? 2 reactions were there and the reaction in horizontal plane is HA, it will be 0. So only one reaction will be there, VA. And in case of roller support, only one reaction was there. It will remain as it is because it was in vertical plane. So dear friends, our aim is to calculate all these reactions. So if I write a beam, this is a beam, this beam is there. It is carrying 2D loading. So friends, how many reactions may develop? At fixed support, 3 reactions will be there, 1, 2 and 3. At roller support, only 1 reaction, and at hinge support, only 2 reactions, right? Now if he shows loading also, if he does not show loading, it means loading is in general. So we will talk about general case. But if he shows loading is vertical only, means if he shows like this, it means he want to say that loading is vertical only and case is 2D. It means if loading is vertical only, all the horizontal reactions or all the reactions in horizontal plane will become 0. So at fixed support, this reaction will be 0. So these 2 reaction will be there. Here 1, and now this reaction will be 0. So this is the case. But if he says this structure as 3D, the same structure, he writes that the loading is 3D. Loading is 3D. In 3D, 6 reactions, 1 reaction, 3 reaction. But if he shows in 3D, loading is vertical only. Loading is vertical only. All the reactions, horizontal reaction, of these 6 reactions, 3 are horizontal. 3 are in horizontal plane. So only 3 reactions will there. Here 1 was there. Here of these 3 reactions, only here was 3 reactions. Only 1 is in vertical plane. 2 are in horizontal plane. right? So this is the way how to show the reactions. But friends, now he says how to calculate these reactions. In order to calculate these reactions, we need equilibrium equations. So equilibrium equations in 2D. In 2D case, equilibrium equations are three: summation fx0, summation fy0, summation mz0. But if loading is vertical only, so horizontal reactions will be zero. Hence, all the horizontal equations will also vanish. They are of no use, because if there is no horizontal loading, what will be the use of this horizontal reaction? However, horizontal equation are there, but they are of no use. We cannot find out anything using the horizontal reaction. Hence, the equilibrium equations will be two. What are those two reactions? Summation fy equal to 0 and summation mz equal to 0. But here summation fx equal to 0, summation fy equal to 0, summation mz equal to 0, right? But in case of 3D, equilibrium equations are 6. What are those 6 equations? Summation fx0, summation fy0, summation fz0, summation fx0, summation fy0, summation mx0, summation my0, summation mz0. But if in 3D loading is only vertical, the equilibrium equations will remain 3, because of these six equations, three equations which are in horizontal plane will be of no use, because the loading in the horizontal plane is 0. Hence, the equation which can be applied in horizontal plane will be of no use, right? So, but friends, how to calculate these equations, these reactions? I take an example, right? If this is an example, this is hinge support, this is roller support, this is again hinge support, this is fixed support, right? I say that how many are the external reactions? So I say 3 reactions here if it is 2D loading, 2 reactions here, 1 reaction here, 2 reaction here. So total external reactions, total unknown external reactions equal to 3 plus 2, 5, 6, 7, 8. These are 8. But equilibrium equations are only 3. What are those? Summation fx0, summation fy0, and summation mz0. Dear friends, it means the equations are 3 and unknown are 8. So we cannot find out these 8 equations, these 8 reactions. These external reactions are represented as RE. R means reaction, E means external. So these external equations cannot be find out using static equations of static equilibrium. Dear friends, equilibrium may be static as well as dynamic. Dynamic equilibrium means a vehicle is moving with constant velocity. It is in dynamic equilibrium. And if a structure is standing in its standing condition, it is in static equilibrium. So we are using the conditions of static equilibrium in 2D. The equations of equilibrium, static equilibrium, are 3: summation fx0, summation fy0, summation mz0. It means we cannot find out these 8 unknown equation, because there are 8 unknown, 3 equations. So only 3 unknowns can be find out, 5 cannot be find out. So we can find out degree of indeterminacy, means this structure is indeterminate, means we cannot determine the external reactions. So the number by which the means we need 5 more equations, then only 3 equations are there and 5 more equations. So total equations will be 8 and total unknowns will be 8, then only we can find out these equations, these unknowns. Hence the extra equations required for analyzing the structures are called as the degree of static indeterminacy. So what is the degree of static indeterminacy? So it is called as, it is of two types. What is our need? Our first need is to find out these external reactions. Once we are in position to calculate the external reactions, now we will start to calculate the internal forces. Maybe that we are not in position to calculate the internal forces, so we need some more equations. So it will come under the internal degree of static indeterminacy, but it is the external degree of static indeterminacy, right? External degree of static indeterminacy. So DSE, external degree of static indeterminacy, means unknown reactions minus equilibrium equations. So unknown reactions we can count, 3 plus 2 plus 1 plus 2. So it will be Re minus equilibrium equations are 3. So this number is called as DSE. Means DSE, static degree of external indeterminacy. Static degree of external indeterminacy means how much indeterminacy is there in calculating the external equations. So it is called as DSE, external degree of indeterminacy. It will be Re minus 3. It is the case of 2D. Now if it is 3D case, Re again we will calculate. If it is 3D, so these will be 6, here will be 3, here will be 1, here will be 3. So we can count Re. So we will write Re. Unknown will be Re minus known. In case of 3D, equation of equilibriums are 6. So this is the formula in case of 3D. But if in case of 2D, if loading is vertical only, again we will count Re. If loading is vertical, so here will be 2, here 1, here 1, here 1. So Re we can count. We will write Re here, and minus, in case of 2D, equations of equilibrium are 2 only, because equation in horizontal plane will become 0. Similarly, in case of 3D, in case of 3D and loading is vertical only, the equations will be out of 6 it will be 3, out of 3 it will be 2 and 1 and 1. So it will be Re minus 3. Dear friends, we can conclude that the vertical loading in case of 3D, if loading is vertical, it can be the similar case as the general loading in 2D case, right? So 3D vertical loading is equivalent to 2D general loading, right? So this is the formula of calculating the external degree of indeterminacy, right? If I take an example, right, for example, this is the example. He asks, what is the external degree of static indeterminacy, DSE? So my first aim is to find out what type of structure is there. If nothing is mentioned, it seems to be 2D, so we can say that it is 2D loading, right? Loading will be 2D, nothing is mentioned. Hence, so it will be, the reactions will be fixed support 3 reaction, it is guided roller 2 reaction, hinge 2 reaction, and it is roller 1 reaction. So Re will be 2 plus 3 5 6 7 8. Re will be 8. So DSE will be Re minus 2D loading, hence 3. So it will be 8 minus 3 equal to 5, right? Similarly, if I take an example like this, it is a frame nothing is mentioned. So it seems to be 3D frame. It seems to be 3D frame. So external reactions will be at hinge support 3, at fixed support 6, at fixed support 6, at roller support 1. So RE equal to 12, 13, 14, 15, 16. RE will be 16. So DSE will be RE minus 6. So 16 minus 6 equal to 10. Means 10 more reactions are required to find out the 10 more equations are required to find out the external reactions, the right. So in this manner we can calculate the external reactions, right. Now we talk about how to find out internal reactions, right. Dear friends, if I talk about the types of structures, so there are mainly two types of structure. One is the rigid jointed structure and second is the pin jointed structure. Means on the basis of arrangement connection of the joint. If two joints are welded, two members are welded at a joint, it is called as rigid jointed structure. For example, building frames or beams. Pin jointed means if joints are pin connected, means on the at a joint two members are connected using pin, right. So it is called as pin jointed structure. There is an assumption in pin jointed structure that loading example of pin jointed structure is truss. So in case of pin jointed structure, there are some assumption that all the joints are pin connected and frictionless, and loading is applied only on the joints. Members are weightless. Under these assumptions, we can say that there is no bending of truss member. Hence, of the three forces or of the six forces, dear friends, in case of frame, if 2D loading is there, so internal forces may be at most three. One will be shear force, other will be bending moment, and third will be axial force. But if it is 3D case, the total forces will be 6. Here, see, this is axial force Fx along the axis, and these two forces in the transverse direction or parallel to the cross section are called as shear forces. Fy and Fz are shear force. Fx is this is axial force. Now these three moments, this is if see, if cross sectional area rotates about the longitudinal axis, so the external moment is called as torsional moment. See, if this beam, due to this moment, the area, this is the moment like this, so area will rotate like this. This is the area, so it is rotate like this. This is the longitudinal axis, so area rotate about this axis, so it is this mx moment is called as torque. But due to this moment, the area rotate about this like this, and due to this moment area rotate like this. So these two moment my and mz are called as bending moment. So in 3D case, we have at most six internal forces. We have at most six internal forces. Two are shear force 1, shear force 2. One is axial force. Two are bending moments, bending moment 1, bending moment 2, and one is torsional moment, right. So in case of 3D, if we make a cut in the structure, so we have to show these six forces. So these six forces are unknown forces in case of rigid jointed structure, and in case of 2D only three forces will be there like this. One will be shear force, other will be axial force, and this will be bending moment, right. But in case of trusses, if loading is only on the joints, all the joints are pin connected and frictionless, member is weightless, so there is no bending of truss members. Hence the shear force and bending moments will be zero and only axial forces will appear. So in case of 2D, only one axial force is there. So in truss member, in 2D, only one force will be there, and it is the axial force. And in case of 3D, again one axial force is there. So in 3D also only one axial force will be there, right? So if there are m members, we will count how many members are there. If there are m members in a truss, we will count the members. So in each member only one unknown force is there. So how many unknown internal forces? M into 1. So unknown internal forces in case of truss, either 2D or 3D, will be M into 1. But in case of rigid jointed structures, if structure is 2D, if there are m members, in each member 3 unknown forces are there: shear force, bending moment, axial force. These force we have to calculate. So these are the unknown force. If there are m members, so the total unknowns will be 3m in case of 2D, and in case of 3D, in each member there are 6 unknown forces, and in each member there are 6 unknown forces. If there are m members, so total unknown forces will be 6m, right? So these are the internal forces. Now how these internal forces are calculated? If we see the method of analyzing the structure, so the method of analyzing is the equilibrium method. Equilibrium method means we will cut a small part from the structure and detach this part from the structure, separate this part from the structure, and now we will write the equilibrium equations of this structure, this small part. For example, this is a structure, this is a structure. Now we will write the equilibrium of small part. Usually we write the equilibrium of joints. So if I cut this joint, so we will make two cut, one is here, one is here, then only this joint may be taken separately. Now I will write this joint here. So if it is 2D, if structure carries 2D loading, so at every location one cut is here, one cut is here. So 3 internal forces here, one is axial force, other is shear force and the bending moment. 3 here, axial force, shear force and bending moment. So 3 unknown these and 3 here. So total unknown forces are 6 because there are 2 members, one is this and other is this. How can we calculate it? Now we have how many equations? 3 equations: summation fx0, summation fy0, summation mz0. But unknown are 6, so degree of indeterminacy here is 3, means 3 forces are unknown. Usually we write the joint equilibrium. So if we have j joint in the structure, j joint in the structure, so in case of 2D, in rigid frames, in case of 2D, equilibrium equations at a single joints are 3. So if there are j joints, so total equilibrium equations will be 3j. And if it is 3D, so and there are j joints, at every joint we will have 6 equilibrium equations, and these 3 equations are what? Summation fx0, summation fy0 and summation mz0. So in case of 3D, the j joint, the equilibrium equations will be 6j. But in case of truss, if I cut the joint of a truss, see this is a truss, and if I cut this joint, so I will show one force like this, one force like this and one force like this, because one is this member, this member, this member. In each member we will show only one force, if it is 2D. So equilibrium equations are 2 only. Equilibrium equations are two only. What are those? Summation fx0, summation fy0. But summation fz0 is also there, but we cannot not apply because there is no use. All these three forces are concurrent, so always summation mz will be 0. So we cannot find out an extra unknown force. So the useful equations are two only: summation fx0, summation fy0. If there are j joints, so total equilibrium equations are 2j in case of truss. But if it is 3D, again if I cut, so in each member there will be one force which is called axial force, but equilibrium equations will be all the three translational equations, that is summation fx0, summation fy0, summation fz0, because all the forces will be concurrent. Hence all the three equations of summation mz0 or mx0 or my0 will be useless. So if there are j joints, so the unknown non equilibrium equations will be 3j, right? So this is the case of truss, this is the case of rigid jointed structures. But if it is beam, it is beam, so again if it is 2D, equation will be 3j, and if it is 3D, equations will be 6j. But if it carries vertical loading, beam carrying vertical loading, now in case of vertical loading, horizontal equilibrium equations will be useless. So in 2D, the useful equations will be 2. So if there are j joints, so equations will be 2j. And in case of 3D, of the 6 equation of equilibrium, 3 in horizontal plane will be useless. Hence 3 will be useful. So equilibrium equations will be 3j, right? So dear friends, if I write one structure, this is a structure, see, this is the structure like this. I want to find out total degree of indeterminacy, ds. Total degree of indeterminacy means how much indeterminacy is in external reactions and how much indeterminacy is in internal forces. Means how many equations are required, total how many total extra equations are required to analyze this structure is called as total degree of indeterminacy. Means how many external equations are required, how many internal equations are required, extra equations. So dear friends, if I write the total degree of indeterminacy, I will write the unknown minus known. And friends, known are only the equilibrium equations, but unknown are Re or member forces. So friends, if in the structure there are M members and there are J joints, now I will write ds unknown. How many unknown? If there are Re equations, so first we have to find this Re, right? So these Re I have to find. If there are M members, in each member, if it is 2D case, in each members there will be 3 forces. So if there are M members, so total unknown forces will be 3M. So these are the total unknowns which we have to find out, minus known are the equilibrium equations. So in case of rigid frames, if there are j joints 1 2 3 4 5 6, so if there are j joints and at each joints there are 3 equations, so if there are j joints, so we have 3 equilibrium equations. So this is the formula to calculate the ds, total degree of indeterminacy, in case of 3D, in case of 2D. But if it is 3D, so unknown are, one is Re, we will count first of all Re. Now if there are M members, in each member there are 6 unknown forces, and total unknown internal forces will be 6M. So total unknown are external equations, external reactions and member forces. But The known equations are, if there are j joints in the structure, so the member force, the equilibrium equations will be 6j. So it is the case of 3D, right? It is the case of 2D beam or frame. But if in the beam, loading is vertical only, so 2D case ds will be re plus x, in place of 3m it will be 2m. So in each member there will be two force only, right? A horizontal one will be 0 minus, and at every joint two equations of equilibrium, horizontal will become 0 minus 2j. And in case of 3D, it will be re plus 3m minus 3j. It is the case of beam carrying vertical loading, right? Now in case of truss, dear friends, in case of truss 2D, so ds will be, if there are, for example, this is a truss, so unknown, if there are re reaction, first of all we will count re, so it will be the re reactions. So re unknown will be re plus, if there are m members, each member will carry one force, so total unknown force will be 1 into m, so unknown will be re plus m. Now if there are j joints, on each joint there are two equations only in case of 2D, because one is summation fx0, other is summation fy0. Summation mz0 will be useless because all the forces are concurrent. However, in case of frame, all the forces are not concurrent at a joint. See here, these forces, the shear force are not concurrent, right? So at this joint, and also this bending moment are not concurrent, so moment equation will be useful, right? So now it is 3D. If it is 3D, ds will be re reaction unknown plus, in case of 3D also only one force will be there, and that is axial force, so unknown will be 1 into m, so unknown member force will be m, so m plus re total unknown minus 2j. At every joint there will be three equations, and all the three will be translational equations, summation fx0, summation fy0, and summation fz0. So it will be 3j. So these are the formulae, in beam, and these are the formulae in case of truss. Okay, now we will solve some numerical on these, right? See dear friends, also one more formula, the total ds is the combination of internal degree of indeterminacy and external degree of indeterminacy. We can easily find out dse and easily find out ds from these formula, and dse already we have calculate, so we can find out dse. If he ask in the question, usually he ask find out total ds of a structure, right? So but sometimes he asks calculate total ds, external and internal. So we will calculate first external, then total, and we will calculate dsi as ds minus dse, right? This will be the useful formula. Okay, now dear friends, I will talk about internal joints. Sometimes some of the joints are released in the structure, means some member forces are released in the structure. How member forces are released in the structure? So internal joints, first I will talk about internal hinge. Internal hinge means, if I take this beam, this is a beam, and now I will break this beam at this point and make the arrangement like this. I make a hole here and make a hole here, and now put this beam on over this and make this type of arrangement. right? Means I hinge here, take a pin and insert a pin inside this, so it will be like this arrangement. So it will move like this is the arrangement. So this arrangement, at this it is called as internal hinge. At internal hinge, bending moment will be zero. How we see bending moment at a point or at a section will be zero? This is I want to check whether bending moment is zero or not. So first of all, I will hold this beam on the left part of this section. I will hold here. Now I will remove all the support in the right directions and hold the structure, the member in this, and try to rotate. If it rotate easily, means here bending moment is zero, because friends, bending moment is the strength of member against the bending. So if it bends easily, means there is no strength, means there is no resistive moment to resist this bending, hence bending moment will be zero. For example, this is a beam, see, this is a beam like this, and this is the internal hinge. I want to check whether here bending moment is zero or not. I will hold the beam firmly at this location, right? And also I will hold the beam firmly at this location and remove all the supports in this direction. I will remove this, I will remove this. Hold it firmly here and try to rotate by this hand, so it will be easily rotated, hence bending moment here will be zero. But if I see at this section, so in this section I will hold the beam firmly here, hold the beam firmly here, and remove all the supports from one direction, either this or either this. So I will remove this support and now try to rotate this beam, so it will not be rotated, hence bending moment is there. Because dear friends, here arrangement, here beam is not broken, here beam is broken. If I show the exaggerated view, you will observe that here is like this arrangement, beam is broken here, here is this arrangement, but here is this arrangement. Beam is not broken here, only a hole is made in the beam and a pin is inserted in this hole, right? So this is, here bending moment is zero, right? So at internal hinge, bending moment is zero. So if at any point some this joint is there, means we have one extra equation, bending moment equal to zero, right? We have one more equation. Indeterminacy means how many unknown forces are there, means how many equations are required, how many extra equations are required. So if indeterminacy, in earlier case, if indeterminacy was 8, means 8 extra equations are required, but one extra equation is this, bending moment equal to 0, means now equations will be 7 equations are required. Means if internal joints are there in these structures, and degree of indeterminacy will be reduced by the same number, right? So dear friends, if it is internal hinge, so two members are connected, so one equation is there, means if two members are connected, so 2 minus 1. So if m dash members are connected at internal hinge point, so it is called as RR, release reaction, means how many reactions are released. Here bending moment is 0, means one reaction is released, so RR will be m dash minus 1. This is the case of 2D. But if it is the case of 2D, 3D, it will be 3 times m dash minus 1. For example, this is a beam, this is a frame like this, right? This is internal hinge, this is internal hinge. So release reaction here are, two members are connected, so 2 minus 1 equal to 1. 4 members are connected, so RR will be 4 minus 1 equal to 3. So total RR is 3 plus 1, 4. Means 4 extra equations are required. We have 4 extra equations, means if in earlier case degree of indeterminacy was 8, now it will remain 4, It will remain 4 because 4 we have some extra equation. So 8 minus 4 equal to 4. If he says this is 3D, loading is 3D, in this case if loading is 3D means RR will be 2 minus 1 into 3. It will be thrice, so it will be 3. Here RR will be 4 minus 1 into 3, so it will be 9, right? So this is the case of internal hinge. Now second is internal roller. What is internal roller? For example, the earlier case was like this. This was the structure. Now I cut the structure here, beam here, and put beam one over other. This is the internal roller. This is internal roller, right? So how many release reactions are there? Dear friends, this is the hinge. So first is the bending moment is 0, and also this, it can move in this direction, so axial force is also 0. However, at this section shear force was there, bending moment was there, axial force was there. Of these three forces, two are released here. Only one force is there, that is shear force. So axial force is 0 because it can move in this direction, right? And bending moment is 0 because it is placed one over other, so it is hinged. So bending moment is 0. So RR in this case is 2. RR in this case is 2. Right? Third, this is internal roller. It is internal hinge. Some arrangement will be like this. Earlier case was like this, but